Fine, let's start. Number 10. In 2012, a team of astronomers took a photograph of something that, by all rights, shouldn't be photographable. Not a galaxy, not a nebula, not a star being torn apart by something massive and hungry. They photographed nothing. Specifically, they photographed the nothing connecting two galaxy clusters called Able 222 and Able 223, a bridge of invisible material stretching between them across tens of millions of light years of open space. They could only see it because of what it was doing to the light behind it. Galaxies billions of light years further away had their images bent and smeared by the gravitational pull of this invisible structure, like looking at a candle flame through the bottom of a wine glass. Map the distortion carefully enough. Work backwards through the geometry. There's your filament. And here's the thing. That filament, that stretch of nothing, contains as much mass as an entire galaxy cluster. It is one of the structural pillars of the observable universe. It is part of what cosmologists call the cosmic web, the vast, foam-like scaffolding of dark matter that the entire universe is draped over, like a wet sheet stretched across an invisible frame that spans billions of light years in every direction. When you zoom out far enough, the universe doesn't look like scattered stars. It looks like a sponge. Vast empty voids surrounded by thin walls and filaments. And at the intersections of those filaments, clusters of galaxies glowing like dew on a spider's web at dawn. That structure, the whole architecture of the observable universe, is shaped almost entirely by dark matter. The galaxies are just the decoration. The dark matter is the building. We can see it. We can weigh it. We can trace where it runs across the sky. We just have absolutely no idea what it is. We built a photograph of the skeleton of the universe. We just can't tell you what the skeleton is made of. Number 9. The year is 1933. A Swiss astronomer named Fritz Zwicky is studying the Coma Cluster, a dense collection of galaxies about 320 million light-years away, and he notices something deeply wrong. The galaxies are moving too fast. Far too fast. By his calculations, the visible matter in that cluster accounts for only about 1% of the mass needed to gravitationally hold the whole thing together. The other 99% is just missing, unaccounted for, nowhere to be seen. He publishes his findings in a Swiss physics journal. He calls the invisible stuff dunkle Materie, dark matter. He is very specific about the discrepancy. He is not saying the numbers are slightly off. He is saying the gap is a factor of roughly 100, not a rounding error, not instrumental imprecision, an abyss. The scientific community's response is, essentially, that's a Fritz problem. For 40 years, the mainstream either ignored the result or attributed it to measurement error. Part of this was the data quality of the era. Spectroscopy in the 1930s was genuinely difficult, and skepticism wasn't unreasonable. But part of it was Zwicky himself. He was famously abrasive, combative, and difficult to work with. He called colleagues spherical bastards, people who were bastards from any angle you looked at them. He was not a man who made it easy to take his side, and so the universe waited. It waited until the 1970s, when Vera Rubin and Kent Ford arrived with better instruments, cleaner methodology, and data from galaxy rotation curves, the speeds at which stars orbit at different distances from the galactic center. The result was the same. Galaxies contain far more mass than their visible stars and gas can account for. Rubin and Ford published. The community listened. Dark matter entered the mainstream. Zwicky had been right for 40 years. He just hadn't been the right person to be right. The thing he found wasn't subtle. The answer wasn't hiding in a decimal place. And for 4 decades, the working consensus was that the problem was the man pointing at it. Science is a human enterprise. That is simultaneously its greatest strength and its most humbling footnote. Number 8. Here's a paradox that takes a moment to fully land. In 2018, astronomer Peter Van Dokkum and his team at Yale announced the discovery of a galaxy called NGC 1052-DF2. It sits about 65 million light-years away. It is, in terms of physical size, roughly comparable to the Milky Way. It contains about 1/200th as many stars, and it contains almost no dark matter, roughly 1/400th of what a galaxy its size should have, by any standard cosmological accounting. A galaxy, with essentially no dark matter. In a universe where dark matter is supposedly the invisible scaffolding that everything assembles itself around. That's like finding a skyscraper with no foundation, perfectly upright, blithely ignoring the situation. There was a rebuttal within months. A competing team argued the mass measurements were based on too few data points to be reliable. That debate settled slowly in Van Dokkum's favor after Hubble follow-up observations in 2021 confirmed the deficit. Then, in 2019, a second dark matter deficient galaxy was announced. NGC 1052-DF4. Same neighborhood, same story. But here's the thing, and this is the part that genuinely bends something in your brain. The existence of these galaxies is now considered one of the better arguments that dark matter is real. The main competitor to dark matter as a theory is modified gravity. The idea that we don't need invisible matter, we just need to revise the laws of gravity at large scales. Maybe Newton and Einstein are slightly wrong in weak gravitational fields. Maybe what looks like missing mass is actually just gravity behaving differently than we expect at low accelerations. But modified gravity is a universal rule. It's a change to the laws of physics themselves. You cannot turn it off in one galaxy and leave it running everywhere else. If the explanation for galaxy rotation curves is modified gravity, it applies everywhere, always, without exception. A galaxy that moves as if it has almost no dark matter, behaving exactly as standard gravity would predict with only its visible stars, cannot exist in a universe where the explanation for dark matter is just tweaked gravity. Because the tweaked gravity would still be tweaking things in that galaxy. The absence of an anomaly is itself an anomaly. So NGC 1052-DF2 is nearly empty of the thing it was supposed to always have. And that emptiness, paradoxically, is the evidence. It sits there, 65 million light-years away, almost hollow, quietly making the case for the very substance it lacks. Number 7. When cosmologists run their best simulations of cosmic structure formation, loading in the physics, setting the initial conditions, pressing play on the universe, the models spit out the same prediction with impressive consistency. A galaxy the size of the Milky Way should be surrounded by a swarm of smaller dwarf satellite galaxies. Not a dozen, not 50, hundreds, possibly thousands. The dark matter halos should be everywhere, seeding small galaxies all around us. For most of the 20th century, we could find about a dozen. That became known as the missing satellites problem, and it was a genuine, serious embarrassment for cold dark matter theory. Either the small halos form, but somehow never accumulate enough gas to build visible stars. Perhaps ultraviolet radiation from the early universe strips them bare, or the model is wrong at small scales in some fundamental way. Both options were uncomfortable. Neither was clean. Then, better technology arrived. The Sloan Digital Sky Survey began scanning the sky with unprecedented sensitivity in the early 2000s and started finding ultra-faint dwarf galaxies that earlier telescopes had simply missed. Then, more surveys followed. The count started climbing. Then, in June of 2024, the Hyper-Suprime Cam on the Subaru telescope published its results, and the conclusion, nearly word for word in the announcement, was that we now face a too many satellites problem. Read that again. We spent roughly 2 decades agonizing over the missing satellites. We built theoretical explanations for why they didn't exist. We wrote papers. Then we found them. And now, there are too many. The universe didn't hand us a resolution. It handed us the mirror image of the original problem, with a patient expression. The simulations are still running. The satellite count is still climbing. Somewhere between not enough and too many is the right answer. We have not found it. Number 6. In physics, when two completely independent lines of reasoning arrive at the same answer, that is usually a sign you found something real. It is called convergence. It is genuinely rare, and when it happens, the community pays attention in a way that goes beyond ordinary excitement. In the 1980s and 90s, two entirely separate branches of physics converged on the same particle. Cosmology needed to explain the observed density of dark matter in the universe. Not just that it exists, but that it exists in precisely the quantity it does. Roughly 27% of the total energy content of everything. The amount is specific enough that it needs an explanation. And certain extensions of the standard model of particle physics, the framework of supersymmetry, independently predicted new heavy particles at the energy scale of the weak nuclear force. When you calculated what those particles would weigh and how rarely they'd interact with ordinary matter, they naturally produced, almost without any adjustment, exactly the right abundance to match the cosmological observation. This was called the WIMP miracle. Weakly interacting massive particles. And it wasn't a coincidence people had to work to find. Two disciplines, doing completely different mathematics about completely different things, tripped over the same number. That kind of convergence, in the history of physics, is how you find the Higgs boson. It's how you confirm the existence of the neutrino. It almost always means the universe is handing you the answer. So the community built detectors, underground labs shielded from cosmic rays under kilometers of rock. The LUX experiment sat 1.5 kilometers underground in an old gold mine in South Dakota, its core cooled to near absolute zero, every possible source of background radiation identified and accounted for. The Large Hadron Collider at CERN smashed protons together at energies high enough to produce new particles if they were there at all. Both experiments ran for years. Both represented billions of dollars and thousands of person-hours of meticulous work. LUX's final result, 0 WIMP interactions. At a sensitivity so precise that a 50 GeV dark matter particle interacting with a cross-section of 2.2 times 10 to the negative 46 centimeters squared would have been detected. The LHC found no supersymmetric particles. Nothing. The room was empty. The miracle convergence. The kind of thing that almost never happens and almost always means you found something true. Pointed at an empty room. Lux Zeppelin, its far more sensitive successor, is running right now under that same South Dakota hillside. The parameter space is shrinking. There are still possibilities, but the miracle is quieter than it used to be. The math is still beautiful. The universe just isn't confirming it. Number 5. The James Webb Space Telescope launched in December of 2021, and within its first full year of science operations, it started returning images that made cosmologists pause in a way that wasn't entirely comfortable. Galaxies. Massive, fully formed, chemically mature galaxies, with stellar populations already billions of years old, sitting just 500 to 700 million years after the Big Bang. In cosmic terms, this is essentially immediately. The universe had barely finished its dramatic opening sequence, and these things were already middle-aged. Stars had formed, lived, and died across multiple generations. Heavy elements had been forged and scattered. The galaxies looked like they'd been there forever. The problem is the timeline. Dark matter doesn't arrive pre-assembled. It accumulates under gravity, starting from tiny quantum fluctuations in the very early universe, slowly collapsing into clumps. Those clumps gradually merging into larger halos, and only once those halos are large and dense enough do they begin to funnel enough gas to start building galaxies with serious star formation. That process, from quantum ripple to mature galaxy, takes a long time. Billions of years, according to our best calibrated models. These galaxies had hundreds of millions of years, and they look like they had billions. One galaxy in particular, cataloged as ZFUDS 7329 and spectroscopically confirmed in 2024 by a team at Swinburne University, contains stars already so old they predated almost everything we'd expect to exist at that point in cosmic history. It was as if you were digging through sediment layers that should only be 10,000 years old and found Roman coins. Not one coin. A collection, neatly arranged. The tension here isn't just numerical. It's structural. Dark matter is supposed to be the thing the universe builds itself around. The invisible scaffolding that goes up first, before the walls, before the floors, before anything. If fully furnished, chemically evolved, massive galaxies were being assembled before the scaffolding had time to grow large enough to support them. We're not dealing with a parameter that needs adjusting. We're dealing with a possible gap in the foundations. Each new observing season, Webb sends back more data. Each time, the problem either holds or deepens. It has not gone away. Number 4. In 2016, a team led by Stacy McGaugh, Federico Lelli, and James Schaumbert published a study examining 153 disk galaxies. Not similar galaxies, wildly different ones. Galaxies spanning many orders of magnitude in stellar mass, ranging from enormous spirals to faint, low-surface brightness systems barely glowing against the dark. Galaxies, billions of light years apart, formed at different times, in different environments, with different histories. At every point in every galaxy, they measured two things. The actual observed gravitational acceleration, how fast things are really moving, and the acceleration you'd predict from Newton's gravity applied to just the visible, baryonic matter, the stars and gas. No dark matter included, just what you can see. What they found was almost unsettling in how tight it was. Across all 153 galaxies, across every radius measured in each one, those two numbers were connected by a single precise relationship. Not a rough trend with scatter you could attribute to galaxy variation. A clean, universal law. The same formula, working everywhere. Now, you could explain this. Dark matter simulations, with enough parameters and careful enough modeling, can reproduce this correlation as an emergent feature, something that falls out of how baryons and dark matter halos co-evolve over billions of years. That's the mainstream interpretation, and it's not unreasonable. But here's the thing. The specific acceleration scale at which the relationship pivots, the particular value where observed gravity starts diverging from what visible matter alone would produce, is approximately 10 to the negative 10 meters per second squared. That number had already appeared in physics once before. In 1983, Israeli physicist Mordechai Milgram proposed a modification to Newton's gravity as an alternative to dark matter entirely. His theory was called MOND, Modified Newtonian Dynamics. It had essentially one adjustable parameter. That parameter was 10 to the negative 10 meters per second squared. Milgram chose it to fit a handful of galaxy rotation curves available at the time. 33 years later, a dataset of 153 galaxies, assembled with no reference to Milgram's choice, independently reproduced his number with remarkable precision. And it gets stranger still. That acceleration value is approximately equal to the speed of light multiplied by the Hubble constant, the number that describes the expansion rate of the universe. In other words, it is the acceleration scale set by the size and age of the observable universe itself. The number that shows up governing individual galaxy dynamics also connects numerically to the cosmological horizon, to the edge of everything we can see. Nobody has a clean explanation for this. LCDM simulations can produce the correlation. They have a much harder time explaining why the pivot point matches a cosmological constant. Modified gravity theorists argue it's not a coincidence, it's physics. Both sides have published extensively. Neither has closed the question. There is a specific number written into how matter moves in galaxies. The same number reappears at the boundary of the observable universe. It was guessed, in isolation, 40 years ago, from a handful of data points, and it has not gone away. That is either a very deep coincidence or a very important clue. The universe is not telling us which. Number 3. Under the Gran Sasso Mountain in the Apennine Range of central Italy, about 1,400 meters below the surface, there's a laboratory shielded by enough rock to block almost everything the universe fires at it. The DAMA experiment, and its larger successor, DAMA, Libra, has been running there since the late 1990s. About 250 kilograms of sodium iodide crystals, kept cold and dark, listening. And every single year, it hears the same thing. A slow, rhythmic variation in detection rate, signals rising through late spring, peaking around the 2nd of June, falling through summer and autumn, bottoming out in December, then rising again. Year after year. The same shape, the same timing, the same amplitude. 25 years of data. The statistical confidence of this annual modulation is 8.2 sigma. In particle physics, 5 sigma is the threshold for claiming a discovery. The Higgs boson was announced at 5 sigma. Gravitational waves were announced at 5 sigma. 8.2 sigma is not a hint. It is not a statistical fluctuation. At 8.2 sigma, if this result came from any other experiment in any other field, we would have moved well past debating its existence and into arguing about the mechanism. The DAMA collaboration's interpretation is straightforward. The solar system moves through the galaxy. The galaxy is suffused with a dark matter halo. As Earth orbits the Sun, its velocity relative to that halo changes. In June, Earth is moving in the same direction as the Sun's motion through the halo, so we're moving fastest into the dark matter wind. In December, we're moving against it, effectively slower. If dark matter particles occasionally scatter off atomic nuclei, you'd expect to detect more of them in June than in December. The modulation would look exactly like what DAMA sees. But here's the thing. The ANAS experiment, running in Spain, used the same target material, sodium iodide crystals, and the same detection method. It ran for 3 full years and found no annual modulation signal. None. Not a hint. 0. The LUX experiment, running 2 kilometers underground in South Dakota and using liquid xenon as its detection medium, sat down and calculated exactly how many dark matter events it should see if the DAMA signal were real. The number it arrived at was approximately 1,550 events over its run. It detected 0. So the situation is this. Either DAMA, across more than 2 decades of continuous operation, with a signal at 8.2 sigma, is wrong. Systematically, fundamentally wrong in a way that has produced a perfect annual modulation mimicking the exact signature of dark matter, year after year, without anyone identifying the source of the error. Or every other dark matter experiment on Earth, using different materials and different methods in different countries, is missing something fundamental about how dark matter interacts with matter. One of those is true. We have not determined which. The detector is still running under the mountain. Every June 2nd, the signal peaks again. And somewhere in Italy, the data keeps accumulating, and the number stays stubbornly, maddeningly high. Number 2. On the 14th of August, 2006, a paper was published that was described widely and with genuine excitement as the definitive proof of dark matter's existence. The subject was a collision between 2 galaxy clusters cataloged as 1E0657, 56. The collision had produced a shape in the X-ray images that looked vaguely like a bullet in flight. Everyone called it the bullet cluster. Here is what happened during that collision. Two massive clusters of galaxies, each containing hundreds of individual galaxies, vast clouds of superheated gas, and presumably enormous dark matter halos, passed directly through each other at enormous speed. The individual galaxies barely interacted. Galaxies are mostly empty space, and the odds of two stars directly colliding during a galaxy cluster merger are essentially zero. So the galaxies passed through like two swarms of bees flying through each other. But the hot gas, the diffuse plasma filling the space between galaxies, which represents the majority of visible, ordinary matter in both clusters, collided. It slowed dramatically. It heated to hundreds of millions of degrees. It compressed and glowed in X-ray wavelengths, forming a bright clump sitting between where the two clusters ended up. If dark matter exists as a collisionless particle, something that barely interacts with itself or with ordinary matter, then the dark matter halos from each cluster should have sailed straight through, just like the galaxies, leaving the gas behind. The mass and the gas should have separated. When astronomers mapped the gravitational lensing, the bending of background light that reveals where the actual mass is concentrated, that is exactly what they found. Two regions of invisible mass, sitting well away from the X-ray bright gas, clearly separated from it. The collision had physically pulled the mass and the normal matter apart. You could see it. For a brief, exhilarating moment in 2006, the dark matter question felt settled. But here's the thing, that was nearly 20 years ago. The bullet cluster has been under continuous academic challenge almost from the beginning. Within a year of publication, researchers supporting modified Newtonian dynamics had published papers arguing that the lensing observations were also consistent with MOND, combined with a population of massive neutrinos. Further analyses contested the mass distributions. And the collision speed itself, the property that makes the event so visually dramatic and so clean as evidence, is considered by a significant number of cosmologists to be implausibly high even under standard cold dark matter models. The very thing that makes the bullet cluster beautiful as evidence might be an independent problem for the theory it's meant to support. In April of 2025, just weeks before this video, a new paper was posted on the physics preprint server arguing that MOND remains fully consistent with every observation the bullet cluster provides. The most famous piece of evidence in the dark matter debate has a counter citation count almost as long as its citation count. The definitive proof has spent 2 decades being definitively disputed. That is not how slam dunks are supposed to work. Somewhere in the southern sky, 1.37 billion light-years away, two things the size of galaxy clusters passed through each other without touching, and we are still arguing about what it means. Number 1. There is a version of dark matter that some physicists take seriously. Published in peer-reviewed journals, simulated on supercomputers, tested against real observational data from real telescopes. That is so conceptually strange, it makes everything else on this list feel almost sensible by comparison. It starts, as so many things in this story do, with a problem. The standard model of cold dark matter fails at small scales. Galactic centers don't have the density spikes the simulations predict. Small satellite galaxies don't behave the way they should. So certain physicists asked a precise question. What properties would a dark matter particle need to have in order to smooth those small-scale failures away? What would fix this? The answer they arrived at was a particle with a mass of approximately 10 to the negative 22 electron volts. To understand how small that is, consider this. An electron, one of the lightest particles we know to exist, has a mass of about 511,000 electron volts. This proposed dark matter particle would be lighter than an electron by a factor of roughly 10 to the 28th power. It is so light it is almost not a particle in any intuitive sense. It is closer to a sustained trembling in a quantum field than to anything you'd recognize as matter. And at that mass, quantum mechanics does something that has no real analogy in everyday experience. The de Broglie wavelength of the particle, the spatial scale over which its quantum nature becomes important, the scale at which it behaves as a wave rather than a point, would be approximately 1 kiloparsec, 3,260 light years, give or take. The quantum wave function of a single particle would span the entire central region of a galaxy. In ordinary quantum mechanics, we talk about electrons having wave functions spread across the diameter of an atom, about 1 angstrom, about 10 to the negative 10 meters. In this model, the wave function spans 3,000 light years. The numbers are not slightly different. They are different by a factor that is difficult to write without feeling slightly unwell. And because there are incomprehensibly many of these particles, all forced by quantum statistics into the same lowest energy quantum state, like a Bose-Einstein condensate, the exotic quantum state that physicists create in labs by cooling atoms to within billionths of a degree of absolute zero. The entire dark matter halo of a galaxy would behave not as a collection of individual particles, but as a single coherent quantum object. One thing, described by one wave function, with quantum interference patterns running through it and vortices, quantum whirlpools of near-zero density around which matter slowly orbits, on scales of thousands of light years. This is called fuzzy dark matter. And if it is real, the Milky Way's halo is not a swarm of particles in the way we usually imagine. It is a single quantum entity, gently waving, threaded with invisible structures that the Schrödinger equation, the equation we normally apply to particles smaller than atoms, would be necessary to describe. Structures you could, in principle, point to on a clear night and say, that region there is a quantum vortex. The Schrödinger equation governs that. Now, here is the thing, and this is the part where everything arrives at once. The mass range that solves the small-scale galaxy problems, that smooths the galactic centers and suppresses the excess small halos, is the same mass range that breaks the large-scale structure data. Specifically, a particle that light suppresses the formation of structure in ways that contradict what we observe in something called the Lyman alpha forest, the pattern of hydrogen absorption lines in distant quasar spectra, which serves as a map of how matter was distributed in the early universe. Make the particle light enough to fix the galaxies, and it predicts too little large-scale structure. Make it heavy enough to fix the large-scale structure, and it stops fixing the galaxies. The cure and the disease live at the same address. The most beautiful proposed solution to dark matter's small-scale failures requires the universe to be quantum on the scale of galaxies. And that version of the answer is, simultaneously, among the most conceptually staggering ideas in modern cosmology, and almost certainly wrong in precisely the way it needs to be right. We have been looking for dark matter for the better part of a century, since Zwicky counted galaxies in the Coma cluster and got a number that didn't add up. We know it's there. We can see its gravitational signature on the largest structures in the universe and on the smallest dwarf galaxies orbiting the Milky Way. We've mapped its filaments. We've weighed its halos. We've watched it separate from ordinary matter in a collision a billion light years away. We just cannot catch it, cannot detect a single particle of the substance that constitutes 27% of everything that exists. And the longer the search goes on, the stranger the candidates get. We started looking for a reasonable heavy particle that barely interacted with anything. We ended up here, at galaxy-scale quantum waves, at a numerical constant that connects individual galaxies to the edge of the observable universe, at a detector under a mountain in Italy that has been measuring a signal for 25 years that no one else can see. The universe built itself out of something. That something is most of the universe. Most of everything you've ever seen or measured or imagined is embedded in it. Every galaxy that ever formed did so because of it. The entire cosmic web hangs on it, and it doesn't seem particularly interested in being understood. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.